Here are the answers to the practice quiz on chemical composition. That includes percent composition, empirical formulas, and molecular formulas. Questions 1 and 2 were just calculating percent composition. So in 1, I wanted the percent oxygen by mass in nitrous oxide. So I want the total mass of both oxygen divided by the total mass of the compound. Now this is the amount of work I would have to show if I were asked to show work. I'd show the mass of the 2 oxygen divided by the mass of the HNO2. That 47.02 grams, that was the total molar mass, adding HNO2 on my periodic table. Now I can tell that this answer is reasonable because it should be a little more than 50% oxygen by mass. Question 2, I had to write the formula. That's fair game. Formula writing is fair game from here on out. That is a skill that we've previously mastered. Now you can look up polyatomics on your polyatomic ion chart, which is also given to you on any assessment. And so the ammonium ion is a +1, the carbonate is a -2. To make that neutral, I'm going to need 2 groups of ammonium. Now, when I want the percent nitrogen by mass in ammonium carbonate, I want the total mass of nitrogen divided by the total mass of the compound. When I have that 2 on the outside of the ammonium group, it means that I have 2 groups of ammonium. Or in other words, I need to distribute that 2 to the nitrogen and the hydrogen. So there's really 2 times the mass of nitrogen, which is about 28 grams, divided by the mass of the whole compound, which does include the 2 nitrogen, 8 hydrogen, 1 carbon, and 3 oxygen. And so again, like this answer is reasonable. I would assume like maybe somewhere around 30% nitrogen by mass. In question 3, an oxide of iron has the formula Fe3O4. If a 14.5 gram sample of this compound is decomposed in the lab, how many grams of iron should be collected? What a great question. Super labby, right? So if I find the percent iron by mass in this Fe3O4 compound, I can start by just using the periodic table. So there's 3 total iron. So 3 times iron is about 167.55 grams, divided by the mass of the whole thing, which is about 231.55 grams, times 100, gives me about 72% iron by mass. Now, there's these laws of composition. One of them is the law of definite composition that says that any form of this Fe3O4 has to have the same composition. Any sample is about 72% iron by mass. So I can take that percentage then, use it as a decimal, and multiply by the mass of my sample. So about 72% of my 14.5 gram sample should be iron, which leaves me about 10.4 grams. That's good stuff. Oh, I love that calculation. Now, number 4 is sometimes kind of a doozy, and there's different ways that you could go about number 4, but this really requires an understanding of empirical formulas. A compound composed of an unknown metal M and oxygen has an empirical formula of MO. So M is going to be some kind of a metal, either sodium, potassium, magnesium, or calcium. Now right there, I could narrow this down to a 50-50 educated guess because I know that oxygen has a -2 charge. And if there's only one atom of metal M, then I know that M must be an ion with a -2 charge. And so right there then, it can't be sodium or potassium because they would not bond with oxygen to form a compound with a 1-to-1 ratio. But magnesium and calcium will both form +2 ions. And so right there, that just helps me out a little bit, that now it's a 50-50 educated guess. Laboratory analysis shows a sample of the compound contains 20 grams of metal M and 8 grams of oxygen. Okay, well, there's two ways to get after this, but here's option one, is to think about this formula as being a 1-to-1 ratio of moles. And on a large scale, if I've got one atom of M and one atom of O, it's the same as saying that I've got equal moles. Moles is a unit that represents a quantity of atoms. So it's got to be a 1-to-1 ratio. Well, I don't know what metal M is, so I can't really convert 20 grams of M into moles because I don't know that molar mass. But I do know the molar mass of oxygen. So I could start with that 8 grams of oxygen. The molar mass of oxygen is about 16, so I could turn that into moles. And from there, I would have 0.5 moles of oxygen. Well, if this is supposed to be equal moles, it's a 1-to-1 ratio, and I know that there's 0.5 moles of oxygen, well, then I know there's got to be 0.1 moles of metal M. So that it's a 1-to-1 ratio of M to oxygen. I know that by looking at the formula. It's MO, 1-to-1 ratio. Oh, okay, so they both have to have 0.5 moles. So from there, you could do a little guess and check, where I kind of set it up the same way I did with the oxygen, that what I want to do is take my 20 grams, and I want to turn it into moles, and I want the answer to be 0.5 moles. Well, you could do a guess and check with the molar mass of magnesium and the molar mass of calcium. Or you could take that 0.5 moles and see, well, 0.5 moles of magnesium, 0.5 moles of calcium, which one would be 20 grams? And both methods would lead you to calcium. The calcium's molar mass is about 40 grams per mole. So if I had 20 grams of calcium, each mole is 40 grams. Yep, that would give me half a mole. So this must be calcium oxide. Now the other option is to calculate molar mass. Molar mass is grams per mole. It's what we would find on the periodic table. And so from there I could say, well, no matter what, I got to do this step here. I got to start with that 8 grams of oxygen and turn it into moles. From there, once I know that it's 0.5 moles of oxygen, then I also know that it's 0.5 moles of metal M. Because of the formula. It's a 1-to-1 ratio in the formula. Well, then you could just calculate the molar mass. It's grams. Well, there's 20 grams divided by moles. And there would have to be half a mole. And then that would give you 40, and I can match that up to calcium on the periodic table. That's a meaty question. That's a good one. I like that one. Good chemistry in there. Then there's a couple different ways that we could be given data to calculate an empirical formula. Empirical formula just means that it's going to be the lowest whole number ratio of atoms. We could be given percentages. So in number 5, I have a compound that's 36.84% nitrogen and 63.16% oxygen by mass. Well, the first step is to assume a 100-gram sample. If I had 100 grams, then I could take those percentages and just convert them to masses right away. Once I'm in mass, I can get to moles. I mean, eventually, I know my formula is going to be like N something, O something. I'm looking for that ratio of atoms. Moles is a unit that represents a quantity of atoms. So you take your percentages, turn them into grams, turn those grams into moles, and from there, you probably get something kind of funky. 2.63 moles of nitrogen, 3.948 moles of oxygen. They're not whole numbers. And so the first trick to try is dividing them both by the smaller number of moles. Right there, you know at least one of them is going to give you a whole number. And then you hope and pray that they're both whole numbers, which I just noticed here that I flip-flopped these guys. Silly me. This is 6,3, right? I know the first one's going to be a whole number 1. You cross your fingers and you hope that the oxygen turns out to be a whole number. Oh, and I got a 1.5. This is like worst case scenario. Usually dividing by the smallest will fix things. I'm so close, but I get a ratio of 1 to 1.5. Well, to keep the integrity of the ratio, now just multiply both by 2. Then I get a ratio of 2 to 3. And that then is a simple ratio. I can't simplify that anymore. I like that. Something kind of similar happens in question 6. We're going to do the same kinds of calculations, but we've just been given a little bit different data. Now we're given grams, like somebody measured masses in the lab. They had a 25-gram sample of a compound analyzed in the lab. It had 6.64 grams of potassium, 8.84 grams of chromium, and the rest is oxygen. So they don't directly tell me how much oxygen, but I can figure it out. The oxygen was released into the air after a chemical reaction. So I know the amount of potassium, I know the amount of chromium. So if I just subtract those two from the original 25-gram sample, the remaining mass should be the oxygen that was released. Now I've got grams of potassium, chromium, and oxygen. And I could just turn them into moles right away. I mean, in question 5, I had percentages, but I wanted to get them into a mass. So we assumed a 100-gram sample. But now you got grams. Go with it. You can take those grams and turn them into moles right away. Now from here I got 0.17 moles of potassium, 0.17 moles of chromium, and 0.595 moles of oxygen. I divided them by the smallest, and obviously the potassium and chromium are probably a 1-to-1 ratio. And we still didn't get perfect whole numbers. I got 3.5. It's fine. From here I can just multiply them all by 2 again. So I get ratios of 2 to 7. So it should be this guy. K2CR2O7. And right there is the 2 different ways that you'd probably be given data to calculate an empirical formula, either through percent composition or maybe just grams, masses that were directly measured in the lab. 7. If an empirical formula of a compound is NO2, which of the following could be a possible molecular formula? A molecular formula should just be a larger version of the little empirical ratio. So my empirical formula has a 1-to-2 ratio. Any multiple of that could be a possible molecular formula. So it could be N2O4, N3O6, N5O10, and so on. Which is kind of similar to question 8. Which of the following shows an empirical formula, a molecular mass, and a molecular formula? Okay, well, number 1, the first 2 choices aren't even proper empirical and molecular formulas. That if I have an empirical formula of HO, then the molecular formula needs to be some larger version of a 1-to-1 ratio. So maybe H2O2. But H2O would not simplify to HO. Same kind of idea with the second choice. C3H8O would need to have some larger version of that ratio to become a molecular formula. Not just adding an extra oxygen. I would maybe have to like double everything. So it could be C6H6 16O2. Okay, so then I'm really down to just the last two. If I had a 1-to-1 ratio of carbon to hydrogen, then a molecular formula could be something like C13H13. But then if I calculate the mass, it's not 78 grams. So that leads me to my last choice. If I had a 1-4-1 ratio of carbon to hydrogen to nitrogen, a true molecular formula could triple that to be C3H12N3. And that does have a mass of 90 grams per mole. The little empirical formula would have a mass of 30 grams. And so if I triple the ratio, I should triple the mass. And then finally, let's calculate some molecular formulas. So question 9, the empirical formula is CH. But the true molar mass of the compound is about 104.1. So all we got to do is add up the little empirical formula's mass. So carbon and hydrogen are about 13 grams per mole. And then we'll compare that to the big molecular mass that has to be given to us. So the true mass is about 104.1. If I divide by the little empirical mass, you should always get a whole number multiplier. Take the large mass, divide by the smaller mass of the empirical formula. My multiplier is 8. So then instead of a ratio of 1-to-1, the ratio is 8-to-8. The most work ever would come in something like 10, where I have to figure out the empirical formula first and then convert it to a molecular formula. And these are all the steps that I would want to show if I had to show my work. So I've got percentages, percent carbon, hydrogen, and fluorine. So assuming a 100-gram sample, I can convert those percentages to masses and then get the grams into moles. None of them are whole numbers. 3.8-ish moles of carbon, 5.1-ish moles of hydrogen, 2.5-ish moles of fluorine. And again, at that point, when you're calculating moles, I would suggest leave a couple decimal spots. If you round them a little too aggressively, then when you're trying to divide by the smallest to get a whole number ratio, some of them might still come out to be a little bit funky. But then you'll find, oh, if I leave a few more decimal spots, I get nice whole number ratios. So in green, that was my next step. Divide each by the smallest, and I got a ratio of 1.5 to 2 to 1. So to keep the integrity of that ratio, we have to multiply everybody by 2. I can't just multiply one of them. That would change the overall ratio. I gotta multiply them all by 2. Then I get a little empirical formula of C3H4F2. And that is a simple ratio. I cannot simplify that any further. So I just quickly added the molar mass. Looking at the periodic table, I got about 78 grams per mole and compared that to the true molar mass of the compound, 156. Again, that has to be given to us. So you divide the larger molecular mass by the little empirical mass, and you should get a whole number multiplier. I got a 2, which then means that I should double the ratio. So instead of the ratio being 3:4:2, we get C6H8F4.